Welcome to the Pod of Inquiry, pushing the envelope for human understanding and optimization, the podcast for podiatrists. The Pod of Inquiry is designed to empower you with knowledge. What happens from there is up to you. Your host, Dr. Stephen Barrett, has designed this show to take you down some very deep rabbit holes, hopefully bringing you back out again, relatively unscathed, but cerebrally whipped, enabling a better understanding of all things worthy of inquiry. If you have more questions after the show, then that is good. The new discovery today many times was the new discovery 50 years ago, only to be suppressed or plainly ignored. Medicine and surgery can sometimes take a long while to get their paradigm shifted. We hope to have a lot of fun on this show and maybe destroy some ridiculous dogma along the journey. Thanks for joining the show today. Let's start spelunking.
Hello, fellow spelunkers. I'm happy to bring you this wonderful conversation I have had with a true scientist. Today's guest is Robert Dennis, PhD. Dr. Dennis is a mechanical engineer and has his PhD in biomedical engineering from the University of Michigan. He was recruited by NASA to work on the team in the development of the International Space Station with a focus on growing human nerve cells in a microgravity environment. Specifically, NASA's interest was to evaluate the effect of electromagnetic energy on tissue cultures. Interestingly, Dr. Dennis was initially a skeptic of PEMF, Pulse Electromagnetic Fields, and began his tenure with NASA with a very negative bias regarding the benefits of magnetism on cellular function. I had such an interesting conversation with Bob that we went longer than expected, and truthfully, I could have spent many more hours with him. Because of the length of our visit, I've decided to break this wonderful experience into 2 episodes. And I most likely will have Bob back for more discussions, as I really appreciate his insight and candor about medical research and scientific methodology. More concisely said, he tells you what's real and what's not in medical research. Dr. Dennis is the founder of Micropulse, a manufacturer of PEMF devices for patient use that is located in North Carolina. I personally have used his technology on myself and have prescribed many units for patients over the last year. I can't say enough about how much I enjoy Bob, how his company has been just a blessing to work with, and I hope you enjoy my conversation with Robert Dennis. Robert Dennis, PhD from Micropulse. Today we're going to talk about PEMF. I've been a follower of Dr. Dennis for almost a year now. I've used his technology. I'm very impressed with it, and he was kind enough to join us today. So, Bob, tell us about how you got here and why we're having this conversation.
Well, thank you very much for inviting me to have this talk. I think we've got a lot in common. We have a lot of things we've talked about offline, and I'm sure, that'll lead to a lot of interesting discussions here. How did I start in this? Well, I didn't. I actually was a mechanical engineer, got a PhD in biomedical engineering from Michigan in the early 90s. And a colleague of mine was a scientist on the soon-to-be launched International Space Station. She was the chief scientist, actually. And she told me there were some people at NASA who could probably use my opinion because of the types of things I built that she knew of for my PhD, my dissertation work. And so I got in contact with them, and they put me in contact with other people. So it's a long line of people that I didn't know. Finally landed on this one guy who was trying to grow cells in orbit. And they call it a microgravity. It's not zero gravity, but it's almost like zero gravity. And cells grow differently there. Everything is different there. Or large organisms, small organisms. They couldn't figure it out. And they were trying to figure out if they could apply some kind of electromagnetic fields, which really was not my area, because I did more tissue engineering stuff. If they could apply some kind of electromagnetic fields to cells to make them grow better. And they were trying to grow human nerve cells on the space shuttle. And I said, well, honestly, I don't know anything about that. what exactly would you like me to do? And they said, well, there's this thing called PEMF. I said, oh yeah, I heard about it. You guys are really grasping at straws here if you're trying PEMF, because that's probably rubbish, but go ahead. What do you want me to do? And so they told me what they wanted me to do, which was nothing much. They just said, can you make the cells grow better? And I said, well, I need to read the literature. And I did. And it was terrible. It was 660 papers of the worst scientific body of literature that I've ever read. Very poorly written, very, very poorly designed science. It was executed poorly, and then was reported poorly. And I estimate that only about 3% of the scientific literature up until when I did this, which is 1995, only about 3% of it was any good to a scientist like myself, which means that you can read it, understand it, and replicate it, and with a reasonable chance of getting the same result. And it did not meet that minimum requirement of being able to be replicated. They just didn't even know what they were doing. So anyway, I told them this. I said, you guys are really wasting your time. This is terrible literature. I don't think there's anything there. And they said at NASA, they said, well, if we pay you money, I said, well, okay, can you make it work? And I said, probably not, but I will try, on the proviso that we do a very carefully controlled experiment, because, pardon me, that's not supposed to be going on. With a proviso that we do a very carefully controlled experiment, and that whatever the data are, whatever the results are, we just live with it. If it's not what you want to see, we don't keep redoing it until you get the answer you want. The answer is the answer. Right. So this is probably the most important thing about me with PEMF, is I started as a skeptic. Healthy skepticism. Okay, I'm open-minded enough to try it, but I don't think it's going to work. So anyway, I read this huge literature, then I designed the experiment. I built all the instruments. I calibrated them all carefully. We ran the experiment at NASA. And there were these tremendous effects on cell growth and, these human neural cell growth. And this is in a lab at NASA Johnson Space Center in Houston. There was these massive effects on cell growth and gene expression and all kinds of things related to, that you could just see with the naked eye, that there's thicker cell mass, which normally, if you can see something in cell culture without magnification, that's like a really big deal. It was abundantly clear. And so I said, okay, this is too much. There's a red flag here. Something is wrong. Let's rerun the experiment. So I redid everything. It was double blind. I mean, it was as controlled as could be within my skill. And we got the same answer. We redid the experiments. We got the same answer. So I published that, and that was published by NASA as well in 2003. And I published something. We can put a link down there if you want to read about it. Yeah. But basically it, just remind me and we'll get a link to it. I published all the technical half of it that they did not publish at NASA. They just published some of the cell culture stuff. And then I published the stuff that tells you what part of PEMF works and what doesn't. And so that really clarified a lot about what types of PEMF work and which ones don't in terms of this particular system we were testing, nerve cells and culture. Right. Short answer is DC, like solid magnets, don't work, sine waves don't work, triangle waves don't work. All that works are square waves and narrow, called delta waves, which is just a very narrow square wave, because they have very sharp on-off edges. As signal goes up, comes back down sharply. And that turns out to be key. And you can eliminate the whole DC part of the signal and just kind of bring it together so it's only an up edge and a down edge, and it works just fine. And so...
So before 2003, I think they were doing some research for transcranial magnetic stimulation in the mid-90s. Is that right? And so would TMS fall under the category of PEMF?
I would put it there. There. And in fact, I've read that literature. And so the problem was that they very early found with TMS that it was having these effects. Right. And, so it's transcranial magnetic stimulation. It was having these beneficial effects on really refractory problems of like PTSD and especially, depression, things like that, refractory. So, and they use the problem was that they found out very quickly that it worked, and then they went right down the FDA chute, which means, okay, when you do something with the FDA, you freeze it and you don't change it, and then you spend 10 or 15 years proving that it works instead of optimizing it and making it work well. This is the unintended consequence of the FDA. And so they made the assumption early on, which is not necessarily true. I was going to tell you about this earlier, that you have to blast the brain with enough magnetism to cause a motor response. So they'll put it over the premotor area, and they keep cranking it up until 110 to 120%. That's the FDA approved level.
Right.
Of what they call the motor threshold.
Motor threshold. Right. Yeah.
So that's enough to make you do this, right?
Right.
And that's why 0.5% of everyone who gets transcranial magnetic, therapy of any kind has seizures.
And you know what? I
out of every 20 people. Yeah.
That we instituted, as I told you before we got on, we put TMS in our practice. We had worked with a neurologist psychiatrist here, and that was standard, is that you would put it over the motor cortex, and you would
premotor cortex,
yeah, and you would stimulate until you would just get a flick in your thumb, and then that was what established your motor threshold. But it was my understanding, and we never saw anybody with a seizure, and I spent a fair amount of time out in San Diego with one of the top TMS guys. And I asked him about seizures, because that's one of the things. And he said, no, I've really never had a seizure. That really happens when they put too much energy over that M1 cortex. But, and even if they do, if you get it off of there right away, they stop the seizure. But I guess, so to circle back then, was it TMS technology that stimulated, no pun intended, NASA's interest, or where did NASA get the interest to do?
No. Well, so I tried to find out from them, and it was pretty much came down to this one guy who was a technician there. He wasn't even the guy in charge of the lab. And he said, well, I don't know. I just heard about it. So the full technical direction that I got from NASA was, I heard about it. It seems to work. We'd like to give it a try. Would you try it?
Interesting.
And I said, okay, let me read the entire literature. And I did. And I said, okay, well, I can break this 660 papers down into, certain types of waveforms, certain, how do you separate out electromagnetism? I have another paper on that. There are approximately, using the FDA guidelines for what's different, what would be a different stimulation? Like, would something that's 10% different be considered different for regulatory purposes? If you plug those numbers in, you get approximately 1 quadrillion different ways to apply PEMF, which is one with like 15 zeros after it. So there's something like 200 million more different ways to apply PEMF than there are known chemicals in the universe. So PEMF is really big and complicated. And that doesn't even cover all the different things you could do with it. In fact, our devices actually do some of these things that are outside of that even. So how do you take something huge and intractable like that? Because it's not been standardized. How do you take something huge and that you can't even, find a place to grab onto it? How do you do that? And that's what I tried to do at NASA, was try to narrow it down and say, okay, it's like the game you could have with, children, 20 questions. Think of anything anywhere in the universe.
Right.
Is it animal or mineral? Okay. And then what you do is, it's called a binary search. You keep cutting the entire known universe in half, and very quickly, like, how many times do you have to cut a Japanese sword in half to get down to a molecule? The answer is about 13. Oh, all right. Okay. And that's why folding it more than 13 times doesn't matter. So somebody tells you some Japanese swordsmith folded something 1,000,000 times, 1,000 times, doesn't matter. You go ahead and do the math. When you start cutting things in half, that's the quickest way to get to the minimum thing. And the minimum thing in the game, 20 questions, is, in the entire known universe, what you're thinking of is a dandelion, a paper clip, the number 2. I mean, how do you get to that in 20 questions? And most children can do it. And it's because you do a binary search. So any computer scientist will tell you that's the fastest way to sort through a data set. If you can get a yes or no answer, a greater than or less than answer, one of those two things, right?
Right.
You can do a binary search on a set of data, and you can take everything in the universe and boil it down to some prosaic, common object, right? That's what I did. So I boiled down something like one with 15 zeros after it down to 6 possible things you could do with PEMF. And it turns out 2 of them worked fine and 4 of them didn't.
Now, I want to get into the biophysics a little bit. And I thought what you said to me before we got on about how complex this really is, I still think it's good just for, a foundational purpose. And so explain some of the concepts, because I know with TMS, we had different programs. We had some that were a different type of burst or a different type of frequency, different, we would use a 10 hertz to stimulate neurons and a 1 hertz to suppress them. So in a depressed area, you would put a 10 hertz stimulus, and in a, and almost always depression would be related to anxiety. And so you would then go to a 1 hertz stimulation. So, but before we get to that, because I think that's really some of the confusion in the PEMF world, is all of these different protocols. And, but so just from a general standpoint, can you explain how taking an electromagnetic force and putting it through tissue converts into an electrical force? And let's go over that a little bit. I think that's real important.
It's a really complicated idea that you can't really understand unless you know a lot of math, but you can state it simply. Okay. When you change a magnetic field, it causes an electric field. So if you're looking at some point in space, anything can be somewhere deep in your tissues, can be floating around out in front of you, whatever. If you change the magnetic field, which means you bring a magnet close to it, you bring a magnet far away, or you put it next to a magnetic solenoid or a coil, you turn the coil on, you turn the coil off, right? When you change the magnetic field, you get an electric field.
Okay.
Right. So if at that point there's conduction, you can conduct through something, copper, biophysiologic fluids, salt water conducts just fine,
Right.
Physiologic saline's a fine conductor. Extracellular, intracellular fluids, they have ions, right?
Right.
You will get an electric field will result in electric current. That's what happens. And this is really well known and understood engineering and physics from like 1864. We've known this very well, and it's called Faraday induction. So that's the physics half of it that we understand really well. And what that means is that one of the upshots of that is that the more rapidly you change that magnetic field, the bigger the electric field. That's
okay. So then by changing the frequency of it's just intensity.
So changing the rate at which you have a magnetic field. So if you've got a magnetic field far from something, say this is a magnet, this is a magnet. So say this is a magnet. If I bring it close, the magnetic field lines get closer and closer. So the magnetic field gets denser and denser at my fingertip. And then it gets less and less. So if I do this sort of sinusoidally, nice and smoothly, the magnetic field goes up and down and up and down. But if I want to get a much bigger electric field, I just move it fast, and I move it fast back, and I move it fast, and I move it fast back. You see? So even you could do that 10 times a second.
Okay.
You'd still be at 10 hertz, but the slow moving one doesn't generate much of a field. The fast moving one generates a heck of a lot of a field. But the slow moving one still generates a field. I mean, that's how induction, stovetops work. That's how motors work.
So if you go to your website, you have the PEMF -ICES, ICES. And give me some insight on that. I know that stands for inductively coupled electrical stimulation, right?
That's a perfect segue. That's why it's called ICES, because it is inductively coupled through magnetism to cause electrical stimulation in tissues. So my argument as a scientist and an engineer, my argument is that PEMF, when properly done, is electrical stimulation. When you do it conductively coupled, that means you hook wire electrodes on and electricity goes through the tissue from one wire through the tissue to the other wire. That's TENS. Okay. Right. That's anything with surface gel electrodes, that you feel the shock. That's conductively coupled. The electrical current couples to your tissues through conduction. There's two other ways to couple current. One of them is capacitively. We don't really do that much, like making capacitors, but that is how your iPhone works. Ever wonder how touching it in different places makes it do different things? Right. You are conductively coupled to your screen, and your screen has little tiny gold deposited on the back into little tiny patches. And when you get close to one of those gold patches, you have a conductive coupling between your fingertip and that gold. That's why it works. That's why you don't even have to touch it. You just have to get close. Okay. Conductive coupling. Inductive coupling is how you transfer a lot of power across space without connecting to it. That's change a magnetic field. Okay, you change the magnetic field. Ooh, big and small, high, high amplitude, low amplitude, or negative amplitude. All right. When you're somewhere in space and a magnetic field is going through you and that magnetic field is changing, you get an electric field that will tend to spin around those magnetic field lines in such a way that the electric field will generate its own magnetic field to counteract that. Nature is trying to stop those magnetic field lines. That's called inductive coupling. That's how your inductive cooktop works. That's how all your really cool gadgets work. There's inductive stuff in everything.
I'm sorry to interrupt, but before you continue with this great conversation, we need to take a quick break to acknowledge this week's sponsor.
This episode is sponsored by Savant Sellers, providers of boutique Tier 1 Reds at a Tier 2 price point. Let's imagine you are spelunking in a cave out in Napa Valley, and you come across some of the juice from Savant Cellars. You may just never want to come out until it's gone. Savant Cellars sources all of their fruit from the really big name boutique vineyards. That's right, where the elites get their fruit. If we put a vineyard designation on our bottles, we would be contractually forced to sell our wines at 3 to 4 times our current pricing. Yes, full disclosure, I am one of the 3 principals, and I'm very proud of our wines. Savant Cellars is the genius of wine. Simply great wines, vintage after vintage, crafted in a Bordeaux style so you can lay them down for years or drink them now. They simply just get better. Use the code SPELUNK15 to get a 15% discount at savantcellars.com. That is CEVANT sellers.com. Spelunk15.
Well, I think one of the interesting things about magnetism when I first started getting involved with TMS was it was astounding how you could deliver this magnetic energy right through the skull a few centimeters deep. Whereas
I'm so excited about that. I'm sorry to interrupt you. Go ahead.
That's okay. No, go ahead. Go ahead.
That's the greatest thing about ICES, about inductive coupling, is that it goes right through skin, right through bone. In fact, I've done some tests on this recently, so I will tell you, you are the first to hear my results, okay? As it should be, theoretically. Right. It even passes through normal healthy tissue, because normal healthy tissue has all of these insulating cells and cell-cell junctions, which are insulators, prevents electric current so that it doesn't drag down your magnetic field. So magnetic field will go through air, dry skin, bone, healthy tissue. As soon as the changing magnetic field gets to an injury where the tissue is disrupted, the extracellular matrix is disrupted, it dissipates energy right there because of the physics. That's what's beautiful about this. So PEMF properly done is self-focusing. As long as you roughly point it towards an injury, it's going to dissipate its energy there, because that's where it can create electric fields, which is why when you first start using PEMF, and you haven't used it before, you feel this electric current, like you and I were talking about, like you felt that on your tibial plateau. And, it's like the reason is there's disrupted tissue there. It's the strangest feeling when you first start using PEMF, because you can feel it right at a deep tissue.
Right.
And everybody keeps thinking of this like conductive coupling, like where you have to put gel electrodes on and maybe they sand your skin a little bit. And then they're like trying to get current to go through, with this like 18th century kind of thing. Well, if you do the math, how efficient is that? And the fact that conductive will always go through the path of least resistance. So it may go through your injury, it may not. Mm-hmm. But induction covers an entire volume of space, and it will collapse into and dissipate its energy into wherever there's most tissue disruption. That's where you want it to be anyway.
So correct me if I'm wrong, but there's only so much energy you can get through a patch on a TENS unit because of the impedance of the skin. So
you're exactly right. The impedance of the skin is so large that it impedes the flow of current, and it gets much larger very quick. So if you have to measure it really fast, like microseconds, then it starts off at like 1,500 ohm, or it starts off at a couple hundred ohms, and it goes way up really fast. So inductively coupled goes right through all of that, and it does its work deep in injured tissue. That's what's going on. And it's just like the perfect way to project energy through all the stuff that you're not too concerned about, including bandages, as long as it's not a sheet of metal, which will dissipate, because you get electric current in metal, right? As long as it's not a conductor, right, with big conducting loops, you can project that energy quite deeply, and that's the beauty of it. That way you don't have to run the PEMF with a huge amount of current, because inductive coupling can be quite efficient, right?
So from a clinical standpoint, now with TMS, we had to be very careful. I think the one contraindication is if they had some type of metallic aneurysm clip or something like that.
No.
And even then, the brain boys would tell me that, well, no, you're way up on the prefrontal cortex. That's back. No worries with that. That's a FDA theoretical contraindication.
Well, an abundance of caution.
Right.
So abundance.
So what if they have, let's say they've had a bad ankle fracture and they have a screw and plates in there. Any contraindication to use?
Well, let me tell you about that, but I just wanted to give you one more number. All right. Okay. When you calculate the efficiency of conductive, like, surface electrodes versus inductive is about 10,000 times more efficient.
Okay.
Roughly.
Right. Okay.
So like in terms of like getting energy to where you want it to be, as opposed to losing a lot of energy, dissipating through, as you correctly called it, the impedance of the skin and skin contact. Yeah, just all your energy gets dissipated there. That's why you feel it there, right?
Right.
So, okay. Now, that being done, you're asking me the question, what about, say, implanted staples, pins, all that stuff?
Right.
Then we talked about FDA, abundance of caution. They're like, we don't know, so don't do it. Okay. Right. So 10 years ago when I started this, more than 10 years ago now, I did the same thing because I don't want to hurt anybody. So I would always say, I wouldn't do it on myself. I mean, if I had a metal pin there or staple or a fixator plate, I wouldn't use it. And that turned out to be, I think, very safe advice. And because I didn't know, it was probably the right advice at the time. But what's wonderful about the people that I try to help, say, like I told you, I'm not a medical doctor. I'm not a clinician. I don't have a license to give people medical advice, right? They're just asking a scientist what he thinks about something. So I'll tell them what I think, with the, caveat that I'm wrong a lot of the time, right? So I told a bunch of people, don't use it there because you have an implanted pin. So a really close friend of mine, who actually was one of my doctoral students, he's a senior vice president and had a big tissue engineering company now. He actually fell off a mountain bike and had some pins in, orthopedic fixation done on his wrist. He had some broken bones there. And he said, yeah, Bob, whatever. I think I'm going to go ahead and try it anyway because I'm kind of desperate. And he did.
Right.
And so he kept a really close log. And he's like, yeah, you can feel it. It's like this tingly feeling. He's like, I can feel the implanted pins and screws for about 2 days. Then he goes, I can't feel it anymore directly. He said, but indirectly, it feels much better. And so he had a combination, mostly titanium, I guess. And then I know at some point in a different location, he had stainless steel. So he was trying it on a couple of different things. And he said that actually the feeling he got was that the pins and everything was less loose. It was more tightly engrafted. And I started thinking to myself, that kind of makes sense because the metal is helping focus the electromagnetic energy doing whatever it's doing. We don't understand the biology, but it's focusing it around the metal implant. And sure enough, everybody who's gotten my advice to say, well, I don't know, I'm kind of cautious. They're like, yeah, thanks, Bob. I'll go ahead and try it anyway.
Right.
I said, okay, every single person who has tried that, I've insisted that they tell me, okay, tell me, what do you think? Every single one said, oh, it was great. It made, I had a loose screw in there and it tightened it up, or I had a loose pin, and they're like, the pain went away. And like, my orthopedic surgeon says, wow, this is growing, engrafting really well. So actually, when I got my left hip replaced 2.5 years ago, that was the first thing I did. I did PEMF treatment before surgery and then within a couple hours after recovery. And I didn't even need to take, the pain pills they had prescribed to me. I handed them back to the surgeon. Said I can get by with aspirin. He was shocked by that.
Right.
And then we did some, imaging and clinical follow-up a week later, and 2 weeks later, he goes, man, you have healed faster than anybody. I said, oh, that shouldn't be too big of a deal. He's like, yeah, but I mean, sometimes I do surgeries on 25-year-olds, you're like 55, you shouldn't be healing this fast. And I had titanium in my left hip. So,
I mean, we have to, when we look at these things, certainly the number one thing is do no harm. And
number one thing is don't harm. Right. But you can do harm by inaction.
Oh, absolutely.
This is the problem that I have with people who are the way I see it is like if you have a committee of 12 people standing at the edge of a pool looking at a drowning person, that's not the time to have a debate whether or not, it would be safe to throw them like a life preserver ring.
Right.
You throw them the ring, you do your best.
Right. Well, and I think this is a little bit tangential, but that is sometimes when you get the best stuff, So I've been recommending PEMF now for a while to our patients, and they'll say, well, I can't feel anything. And I will tell them, well, one of the nice things you include when you send your devices out is the little hexagonal disc that you can put the thing on and it lights up. So it's creating some energy. But yes, exactly. And
that's what it is.
Yeah, and that shows them that yes, there is something really going on, and
you can hear it clicking.
Yeah. And the other thing is I say to them, you've heard about MRIs, right? And they'll go, oh yeah, I've had an MRI or 2 or 3 or whatever. I said, well, that's magnetism. So
same deal.
The magnets going through the body, making things line up so that an image can be obtained. So just because you don't feel an energy source necessarily doesn't mean it's not actually going there and doing things. So I think that's a good analogy for clinicians to use when these patients will say, well, I'm not really feeling anything. It's like, well, that's okay. But let's get back now to the biophysics a little bit, because you have a concept in there called streaming
currents. Yeah.
Streaming currents. Right. So you have these, you talk about how the magnetism goes from a magnetic to an electrical situation, which causes these ions to spin around the cell membrane and maybe within the cytosol itself, as well, probably within the mitochondria, right?
Anywhere where you could imagine a loop. Okay. It will rotate around in a loop. So here's the thing. All right. What induction does is it turns a changing magnetic field, Imagine that magnetic field is coming straight through the screen here. I'll go right through the camera, right? Then that induces an electric field like this. Now, it's an electric field. An electric field induces a force on anything with a charge. Normally, we're thinking of electrons, but that could just as easily be any charged species in the physiologic environment. As you know, there's tons of stuff, right? We have saline solution, just a magnesium, calcium, all kinds of ions floating around. Plus, we have ionic charge on, for example, transmembrane proteins. Right. So imagine my head is a cell. Okay. And I put a magnetic field through that cell. If there's a charge floating around there, it can't necessarily go right through the membrane, but it could orbit around that cell. Right. Because the induction is causing an electric field that's inducing the circular movement of that charge. Now, if that charge is attached to something like a transmembrane protein, it will cause that protein to bend and move, and in fact, may activate that protein by causing it to move.
Right.
We know that, conformational changes in transmembrane proteins can act as a signal. We just know that, right?
Well, that would fall into the piezoelectrical
neighborhood, right?
Could be,
right. But the problem with piezoelectric effect is that it's very low amount of current and it gets grounded out very, very easily. So piezoelectric things, like people talk about collagen being piezoelectric, that's true. When it's dry, you can measure it, but when it's wet, it kind of shorts itself out right away. That's the problem, right? But with induction, electromagnetic induction, you saturate a volume of space with this changing magnetic field, and it induces all throughout that space an electric field that makes free ions want to follow this circular path, and attached ions generate a force to try to, so that induction causes an electrical field that either accelerates a free ion or applies a force to a fixed ion, fixed on, say, for example, a transmembrane protein. And there's tons of transmembrane proteins that would be perfectly sensitive to a voltage-gated channels, or one of them, but that's for a voltage across the membrane. So what we're probably seeing is a voltage along the membrane, paramembranous, right? That's
outside it,
free ions, right? Or changes in the conformation of a protein that's got some charge associated with it, right? Or those proteins are detecting streaming charges. This is this whole streaming current thing, right? And so streaming currents were proposed in the 1970s as a possible mechanism for how is it that healthy tissues such as bone can detect it when you're walking. Your bones get healthier if you walk a lot. You don't have to break them. You don't have to super stress them like weightlifting. Just normal activity actually elicits a functional adaptive response in orthopedic tissues. How? We didn't understand, and we still don't understand exactly how it is that orthopedic tissues transduce, regular low intensity motion. Getting up out of a chair and walking is a lot healthier for you than sitting all day. And we all know that. Why is that true? Part of it seems to be that your body can detect low amplitude physical activity by some mechanism. And one of the mechanisms that's been proposed for about the last 45 or 50 years is streaming currents. Well, imagine you have a sponge and you just gently squeeze that sponge. You're moving water through that sponge, but if that water has ions in it, those ions act as like a current as they flow out of the sponge as you squeeze it. It doesn't have to be super intense, just a nice gentle squeeze on the sponge causes ions to flow. If you have some way of detecting those ions, then you can detect, because the ions, presumably they'd have to move, a net movement. Most of them would have to be going in a certain direction. Then you get a clear signal. Oh, yeah, there's some kind of movement. So same thing in like your articular cartilage, right? How can articular cartilage, which is 90% extracellular, it's only, it's 100, it's 90% extracellular roughly, totally avascular. How can it detect mechanical loads? Well, you're squishing fluid around the cells, right? And that carries ions with it. So I think what's happening, my hypothesis is that PEMF causes ion movement and transmembrane protein deformation because of the induced electric fields. And those those deformations and ion movements simulate normal movement, but the signal of normal movement, but they don't also apply the mechanical loads associated with normal movement. So you get the beneficial signal without the load.
One of the things that I picked up in my research on TMS was that, and they had some really good studies out at UCLA and some of the different places with functional MRIs showing increased blood flow to areas, after the magnet was applied for a certain period of time. There was the hypothesis that more synapses were formed in areas, which I thought was very interesting. And then the other was that some of the Alzheimer's work, they are finding increased glucose utilization, which ties into a whole different discussion. We'll have to get to that some other time. But there are these demonstrable physical effects that you can see with these objective things like functional MRI, actually even some of the very sophisticated EEGs that they do. They'll show an area that's not really very active from an electrical current standpoint and apply the energy, and then it becomes that. So this may tie into this streaming ion concept and how it's working.
There's a couple of things that I think are interesting. So that would work for any kind of cell, a bone cell, a skin cell, cardiac muscle, right? Then there's the second effect of PEMF on excitable tissues. What are excitable tissues? Muscle and nerve, right? So that may actually have a secondary effect that is sort of like a sub-threshold stimulatory effect, which is why I don't think that you necessarily have to. And many people agree with me, by the way, who do this, or I agree with them rather. They're the ones who thought of this, that TMS is generally used way too high, and they really ought to tune it down even below motor threshold. People have shown that it has the same beneficial effects, but people stick with motor threshold because that's what's approved by the FDA. Okay. When in fact, it would be safer to use lower than motor threshold. However, that has not been demonstrated to, a satisfactory level to the FDA that it's just as effective to turn it down some, right? But, it's, if you delve into the literature, there were some recent reviews on TMS that say, hey, we know a lot more now than we knew in the 90s. And you don't need to blast people as much and you still get the same beneficial effect. What the threshold is for effectiveness, we don't know, but it seems to be quite a bit below causing an actual neural depolarization, right?
Right.
We hope you all enjoyed today's show and got some truly empowering knowledge out of it. You can always follow up on anything we talked about in the show notes, found at our website, podofinquiry.com. If this incredible and educational conversation has tickled just a little bit of your cortex, please leave us a review and spread the message to your friends and colleagues. Let's keep spelunking.
This podcast is designed for informational purposes only and does not constitute any medical or surgical consulting advice or imply a development of any physician-patient relationship. The opinions of guests who are featured on the show are not necessarily the opinions of Dr. Barrett or the production team. This podcast is owned solely by Barrett Medical and Surgical Media, LLC. While the show is highly oriented for physicians and healthcare providers, anyone interested in the improvement of human performance and understanding will find this a welcome goblet to sip from, or guzzle. However, no representation or warranties are made in any way whatsoever on this podcast for any products, techniques, or other things discussed. Invited guests are not vetted by the Pod of Inquiry for their qualifications and may have a direct or indirect financial interest in what they present and discuss on the show. The Pod of Inquiry disclaims any responsibility from anything taken from the show and used personally or professionally. It is a responsibility of the listener to perform their own due diligence prior to the implementation of any ideas, products, techniques, or anything talked about on the show.